So now we know a little bit about the amount of substance, it's time to dive right in and talk about how we might establish the formula of our chemicals. Let's get some words straight. A molecule is when we have multiple atoms joined together by some kind of bond, a chemical bond. And that molecule could be an example of a compound if the atoms that are involved are different to each other. Now, we're going to use these words extensively through the rest of this, so you're going to have to get used to them. Now, we could represent what atoms are present in a molecule with a molecular formula. It is basically a shorthand notation to give a picture of what is present. So here's an example. On the right-hand side, you can see a picture of hydrogen peroxide. Now, hydrogen peroxide, in the name, it's given that there's hydrogens there. They're the white atoms, and oxygens. And peroxide normally means it's referring to two oxygens present, the two red atoms. Now, a molecular formula of this must count both the two H's and the two oxygens, and the number of each of those atoms is given in a subscript following the chemical symbol. So H2O2 would be the molecular formula for this. Now, molecular formula are very good at describing small, simple molecules. They're less good if there is a repeating pattern, if the basic unit is repeated many, many times. For example, in large crystalline structures, molecular formula become a little bit cumbersome. They're just basically going to be counting thousands and thousands of atoms potentially. So we have to look beyond molecular formula sometimes to empirical formula. So what is an empirical formula? Well, it is the simplest whole number ratio of atoms that could be found in a compound. Now that sounds quite complicated, but it means this. If I've got multiple repeats, what is a single unit like in that whole bigger structure? So for example here, I've got diamond. Now diamond is just carbon. So the molecular formula could be like carbon, and then count how many atoms it's got and put it underneath. It'd be like carbon 100 billion, billion, billion. That's not sensible. But what we could realize is that each carbon in that crystal is almost exactly the same as every other carbon. In fact, exactly the same as every other carbon in that crystal. So we don't need to count how many there are. I mean, that just depends on how big the crystal is. When it comes down to it, we could just say the simplest repeating unit in this diamond is carbon. Carbon C with a 1 next to it, because that is the simplest repeating unit. Now, some non-metals, for example, carbon and silicon, will form a massive, great big structure, but other things like ionic compounds like salt will form a repeating pattern. The simplest basic unit of that would be sodium chloride, NaCl. On the right-hand side, you can see some molecular formula. And you can see that that is not the simplest whole number ratio of those two. For example, hydrogen peroxide, H2O2, well, we could divide that by 2 and we'd end up with H1O1 or HO as given there. So have a look at the following molecular formula and see if you can work out what the empirical formula must be. Have you understood this? Well, if you have, you should be able to answer these questions here. And the answers are presented here as well. When we talk about the mass of 1 mole of this substance, well, there are different ways in which we could represent it in terms of the symbol that we use, but also what it represents in terms of the mass. Relative atomic mass, if you remember, was a capital A subscript R. But sometimes these chemicals don't exist as a single atom. Sometimes they float around in their particle as a molecule. And so rather than using the relative atomic mass, we'd use the relative molecular mass. And this is a different symbol, but it's fundamentally the same. It's capital M sub R, and then in brackets of the chemical that you're talking about. And simply, it is the sum of the relative atomic masses of everything that is involved in that molecule. Now, giant structures like salt can have their mass expressed as a relative formula mass, but it must be of the empirical formula and not following the molecular formula. Let's talk about crystals for a second. Dioscorides, first described, as far as we know, a chemical that he called chalcanthum, which basically means blue vitriol, which is our good old friend copper sulfate, a gorgeous blue crystal. Now, it turns out with most crystals, to maintain that crystalline shape, there needs to be some water molecules trapped within the crystal structure. This would make it a hydrated crystal, and that hidden water would be the waters of crystallization. Normally, with those crystals, if we continue to heat them, the crystals break apart and it turns into a powdery anhydrous powder. So how do we, when it's in crystalline form, represent that as a formula? Well, here is a really good example. You can see that we've got copper sulfate with 5 water molecules for every copper sulfate molecule. To make that gorgeous blue crystal, we must surround the copper sulfate with water molecules. Of course, if we then go on and heat it, those water molecules come out of the solid, they will evaporate away, they'll basically come out as liquid, and you will end up with anhydrous copper sulfate, which is not nearly so interesting because it's just a white powder. But if you ever see a dot and a multiple of H2O, these are the waters of crystallization, water molecules that need to exist so that a crystal can take its shape. But don't take my word for it, you can go see it yourself. So if you put some copper sulfate in a beaker, and a boiling tube, and you put a bung on it and a delivery tube that takes it in the bottom of a test tube, which itself is placed in some cold water. Then as you heat it, you should find that the waters of crystallization come out of the hydrated copper sulfate, they evaporate out, and what they do is they then condense down in the test tube. So at the end of the process, you can measure the mass of the water that was present and measure the mass of the copper sulfate, enabling you to determine just how much mass was the waters of crystallization. So all of those crystals are basically hydrated salts, and we can always represent this in our empirical formula because, like all of these crystals, there are many more times this many atoms, many repeats of these simple molecules within the overall structure. But we're representing the smallest ratio of hydrated salt to water molecules present in this crystal. There is an experiment that you can do to work out the formula of a hydrated salt. It involves weighing an empty crucible, adding the hydrated salt into it, heating it until it goes white, and then finding the mass afterwards. And basically the mass that has disappeared represents the mass of the water that's evaporated, and then you can find out exactly what mass of water has left. Knowing what mass of water has left, you would then be able to do the mass of the water divided by the relative molecular mass of the water, and that will tell you how many moles of water have left. You could do the same by measuring the mass of the anhydrous copper sulfate. You could find its mass at the end and divide that by the relative molecular mass of copper sulfate to find the number of moles, and then you can compare the number of moles of copper sulfate to the number of moles of water and ascertain the empirical formula containing the waters of crystallization.